Great. Good afternoon, everybody. Good to see you all here. Colleagues, friends, and fellow interested people working on the problem of decarbonization. First of all, I want to thank the chairs for inviting and for all the hard work that has been put in to organize this conference. And in the next 20 minutes, I'm going to share with you the work that I and the team did over the last 2 years to get a deeper understanding of where our future renewable hydrogen could come from. It's a big question, and it's going to be quite some detailed information. But it's great to be up here and to have the conversation together about where these big new transformative technologies are going to come from and where in the world we can expect this renewable hydrogen to emerge. And it's an important question because as we speak, this is not just an academic important topic, but also for policymakers. This is a topic that is very high on the agendas. And I think it's again, getting a lot of attention. And in the coming years, I expect much more of all of us to maybe be working on this topic or related topics. Okay, let's get started. My name is Mei. I'm part of the LITS laboratory here in this beautiful building. And I did this work together with my 3 co-authors, the one presenting today. Okay, what's our challenge? The challenge we're addressing here is, of course, meeting a rapidly increasing energy demand while at the same time reducing our CO2 emissions. This is going to take new technologies and the ramp up of the technologies we already have. So I love that difference that the MIT conference is making, type A and type B. And today we're going to mostly talk about type A, about rapid scale up of solar, wind, batteries, and electrolyzers. And this is a rapid scale up indeed. I looked up the numbers, and as these years, as these technologies are progressing, the rates of build out for the batteries and the electrolyzers is even faster than the build out of solar. And we all know that the solar build out is going at a tremendous pace. China last year reached a terawatt production capacity in solar. That's a number to really make us stop and think where this is going to go in the coming years. First, let's look back. Because only through looking back can we hopefully look forward into the future where this is going to. And this is actually the first large-scale electrolyzer in the world. It's a plant in Norway. It was 135 megawatts at the time, alkaline electrolyzer. And it was used for industry purposes, so ammonia production. And as you see, it's very similar to the modern day electrolyzer, which looks like this, which is part of a 500 megawatt plant that's being built in Texas. And this is the scale level. So hundreds of megawatts that is becoming the new normal for electrolyzer. So, and what is driving this is, of course, driven by this rising energy demand, but also the rapid drop in investment costs. So I'm here showing this cumulative cost drop on the left side. Solar, but also wind, it's coming down on a lot more logarithmic scale, even surpassing the costs of fossil fuels at the moment, and the electrolyzers and batteries are not very far behind. All right. And then policymakers are catching up to this. There's a target for 10 megaton of hydrogen and 10 megaton of hydrogen imports. That should all be renewable for the EU. These are enormous amounts. And this is, of course, driven by the problem of sourcing natural gas in Europe at the moment. Another important development that I want to share and highlight is that Japan has been importing the first hydrogen from Australia. This is a game changer. And it raises the question, how much import and export are we going to see of this hydrogen? But it's going on. And then quite quickly, the question emerges, at least for our team, where are the global low-cost sources? And where can we expect this very large-scale hydrogen to be produced? Let's go into this analysis a little bit more. First of all, I'll share how we are looking and tackling this problem. We've divided the world into a 1.25 and 1.25 degree grid cell. That's about the size of Greater Boston, so 30 by 30 kilometers. And at that grid cell level, we're looking at 10 years of data for solar, wind, and then determine what is the optimal size for that solar PV, that wind turbine, the battery storage, and the electrolyzer system. And then we minimize. We minimize the production cost of producing that hydrogen. And to put that into perspective, I've here put up for us these grid cells, and it's not, an out of this world amount or size, because here we're looking at one of the largest solar plants in the world. This is the Batla Solar Park. It's in India, in the north, and already it's at 3 gigawatt solar. And you see the size, it's in the top of the white box I'm drawing and at the bottom right. And it shows the size of what we are already now building out. And this is just the start. So continuing on the method, because if we are looking at a 30 by 30 kilometer grid size, we have to do that for the total world. And that requires a formulation of the problem that still allows you to optimize every location. So this is how we approached this problem. We have the input data. We first determine the capacity factors, wind turbine, solar PV. Then we determine the daily optimal battery storage, and that goes into the optimizer for each location. And then we're looking at some new technologies as well. So because we're including offshore wind, offshore solar, and also offshore electrolyzers. And here I'm showing a picture. It's from Siemens, where they are testing putting the electrolyzer offshore on a wind turbine. Another example is offshore solar. And of course, we had solar on lakes already. Indonesia is putting up quite a lot of solar on its lakes. But solar offshore at sea is also a technology that's under development. And currently in the Mediterranean, there's a 100 megawatt project in preparation that's off the Italian coast. So this is coming. And I was surprised to see the speed of these developments. All right. And then, of course, we're looking at hydrogen, and we can make hydrogen out of nothing. We need the water to make that hydrogen. And here I'm showing the first map of what water costs are we looking at. And long story short, transporting and producing water, so this would be through desalination, is expensive. However, if you compare this to producing the renewable electricity and producing the hydrogen, it's actually a pretty minor part of your costs. So around 1%, depending on where you are, of course, the globe. This is an intermediary output that you can expect. This is a wind capacity factor overview for the total globe. So not just on land, but here we're doing this for the full Earth. And one thing that struck me was how much wind we actually have on the poles. And if you look at the equator is really way less wind than we have in our temperate regions here, for example, in Boston. And this is a very important factor in the cost drivers for the renewable hydrogen, as we will see. And this is a movie we've made to give you a intuitive understanding, hopefully, of how this system is functioning. So we're looking at the wind turbine capacity factor from before in the lower left, the solar PV capacity factor in the middle, and then the cumulative hydrogen production in the lower right. That's actually the one to look for. And on the top, we see the hour by hour electrolyzer output. And what struck me is actually what enormous capacity rates, so outputs, you could get in the southern latitudes on the ocean. Of course, we're not building there in any sensible way at the moment, but the sheer difference that the wind factor is making on the electrolyzer output. And I think this brings us to one of our insights there, is that wind is a very important part. If you have a good wind resource, that's really going to help you produce a lot of renewable hydrogen. Right. But what about storage? Because storage is in this system setup. Now, we looked at the optimal storage size for every location and at the current economical cost, so the investment cost for our batteries, lithium-ion batteries, we're not seeing any storage being deployed, which makes sense because it's a very expensive part of the whole system, and the storage would actually have the purpose of feeding the electrolyzer. But if we look at very sunny regions, this is one of the most sunny areas on the globe. That is in Chile, the Atacama Desert. Also, we didn't see any storage if we take 2023 values. Only when storage would become about 40% cheaper would it start to make an impact on running the electrolyzer. Okay, let's now look at some of the cost maps. Because I think the cost maps, they summarize what we're looking at, and it helps us to answer the question, where could this renewable hydrogen be produced? And first, I'm sharing here the cost map that shows just the hydrogen production from wind. And next, I'm going to show the map when also solar is included. And I think this difference is a very strong showcase that actually a combined system of wind and solar in a lot of locations, actually most of them, will bring you lower hydrogen costs compared to just wind by itself. All right, let's then go to the final results and try to answer this question. This is the global long-term supply chain, supply cost curve for the hydrogen production. If we look at every country and we sum up how much hydrogen it could produce, at what cost level, we're getting this supply curve. And all the way to the right, we see Russia, with its large landmasses that they could produce most of the hydrogen. But at a higher cost than Canada, Australia, Brazil, the US, or China. But actually, quite a small group of countries would make up that very large potential hydrogen production. The interesting thing, of course, is when we look at the lower left quadrant, let us zoom into that point. So looking at the lower left, where we have the lower cost hydrogen production and actually a smaller scale on the x-axis, we're getting into view, I think, the low cost areas. And the number one location would be with the 2023 values for economics and the technology. It would actually give Chile the lead in being able to provide the low cost hydrogen resources. Followed at about $10 to $15 more per megawatt hour, Canada, the United States, and Australia. And then at some gap, we would see China, followed by the other countries. And that was to some extent a surprise, but also maybe to some extent expected, because Chile has indeed this fantastic wind resource available. The bigger question, or the biggest surprise, was how large is the cost difference going to be? Because can we expect a future where we just as now import our oil and import our natural gas or export our natural gas? Or is the future more like local production of our renewable energy that is not actually exported over that large distances? And I think looking at the cost differences between the countries, I think that highlights or starts to highlight, and it will be the next step of the work, that actually the cost differences do not immediately lead to the conclusion that we will see very large amounts of imports and exports of renewable hydrogen. And with that, I will close off my talk, and I'll give it back to the chairs, and we can have the questions as a result. Thank you, Eric.
Thank you so much. So Professor Forsberg yesterday was talking about the possibility of building nuclear plants close to where the mines are, reduce hydrogen on one side, or using it as a reducing agent. Do you see that scenario coexisting with the wind and solar? And if not, I mean, one of the main arguments of Professor Forsberg was that you would need to ship the mineral to the side of the fuel. Would we push the mineral to Chile in the future, or bring the hydrogen from Chile to where the steel is being produced? What's your take on the relocation of industries?
Right. Yeah. Thank you for that question. I think Professor Forsberg he mentioned and really touched on that crucial insights that actually industry could be reallocating again to the low cost locations, right? And they have been doing so when the US had the boom in shale gas. A lot of the very natural gas intensive companies, they reallocated to the US. In this case, it's part of our ongoing work. So this is the next step. But the big question would first be, how much renewable industrial products can we first expect in the market? So, yeah, but trying to answer your question, because it's a great question, and I don't have all the answers here. But what I would say is, when we look at these differences in costs for renewables, and this is for renewable hydrogen, I think that what we can take away from this is that the cost differential is not so large as to result in a massive transfer back and forth of raw materials. So for aluminum, you would transport your bauxite, your aluminum, all the way to the cheaper electricity sources. But yeah, in this case, I think actually the renewables could be an equalizing feature in the energy systems, and remove, because I'm not seeing the big cost differentials that you would have, for example, oil in Saudi Arabia with a production cost of around $10 per barrel, and let's say Norwegian oil that is closer to $60 per barrel. I'm not seeing that in the analysis so far. Yeah.
So the cost curves that you have there differ from the Hydrogen Council, McKinsey, and ARETA as they look at a mix of the variations of blue and green, and also get into the issue of what is an export market and what's an domestic market. And could you address those? Those differences?
Yeah, thank you, and I will try to.
It's really very interesting, very leader because my question was, okay, you are saying that there will be no flows of hydrogen across the world. Did you consider the domestic consumption? Because of course, if you exceed the domestic consumption, that will be easy to there will be some kind of interchange around the world. I mean, you also consider this aspect of the say the low of hydrogen, the
Right.
consumption.
Yeah, I will try to answer that question.
The other thing I was mentioning, this is pretty visionary. It remembers to be something that has been thought by State Grid Corporation of China. I don't know if you are familiar with global energy interconnection.
Mhm.
They are given point in this huge project in which we said something that to a certain extent is similar. We put the wind power around the North Pole, we do PV in Africa, Australia, we do a large European network. At a given point, the vice president of this organization was Professor Chu from Stephen Chu from the United States. And so they have this idea to share at the world level the renewable. This is fun. The problem was or is not so much technical, but geopolitical. Can you imagine with the end of globalization, if we can share United States, China, Russia, and Europe, the same infrastructure, share at the global level? And I was wondering, do you feel that something like that can also be a problem in this perspective? I mean, the geopolitical dimension, besides the technical.
Yeah, those are. I hear your question. I hear two questions there. I'll try to address them. I'll start with the question from the chair. So, what is important is that here we're taking into account values that are as close as possible to the real world and to industry. What I'm seeing at the moment, from my perspective, is that the values published by IRENA in 2022, they are very much above what is actually offered or auctioned within the market, especially in India, China, Saudi Arabia, but also wind, offshore Denmark, the Netherlands. IRENA is, I would say, very much higher than what was observed in real life. And actually, we had to do. Yeah. Yeah. And I think McKinsey, also responding to McKinsey, I think McKinsey is doing a lot of great work in this space. I think they're ahead of most of us. But I think the low cost that they're projecting for Chile, I would say at around $1 of hydrogen, that's so far below all the validation data points that I gather from industry across the globe, also comparing with another institute, Fraunhofer in Germany, who is doing work on this already for a long time. That I would say McKinsey is a little bit more on the bullish side on hydrogen. That would really require much faster technology ramp downs. And over the last 2 years, with the raw material prices going up, actually wind turbine costs have gone up instead of down. And also the electrolyzer costs have not gone down, but actually stabilized. And I think that will put a kink in the McKinsey curve, so to say. And what we're doing here, we're correcting for cost of capital by country, and we're correcting by country for labor costs. Because putting up the solar panels in a country like the US or in Denmark versus India, China, makes a very large difference, because the labor cost share of solar panels is about 30 to 35%. So a much lower labor cost has a massive impact on your investment cost level. And I think that has to be taken into account to reach real life investment values that we're seeing in the market. I hope that answers the question without going.
Yeah, I mean, the MENA countries, obviously, the data is much more opaque.
Yeah, agreed. Yeah. So, but in the effort, this is going to be published as open data with the goal that all of us and all our peers and colleagues can use this and speed up our modeling, our techno-economic assessments, etc. Yeah. Yeah, there were two more questions here, but I'll leave it to the chair to decide which question to take next. We have two chairs.
We can discuss that.
Yes. Let's do, of course.
I don't think.
Yeah.
Okay.
Should I wait for later?
Yes, I think so, yeah. I'm sorry, just to keep it, because we're down at, where are the, power, what? Yeah, thank you. Thank you very much.
Thank you.